Okay, so taking off from where we left off, we were talking about the drag force on a sphere, on a smooth sphere, when it's moving through a viscous fluid. And so this is what we said, the drag force is linearly proportional to the velocity, right? And the coefficient of viscosity necessarily appears in the expression. I'm simply stating this. We haven't derived this. I encourage you to look up Landau-Lifshitz or Kundu or any other popular fluid dynamics book for how this derivation is done. But it's a very important result, and this particular result is graphically represented in this form. We will return to this in a minute. For the time being, I'll simply tell you what this means in one particular way. And so what's on the x-axis is the Reynolds number. Okay, that's not how this is written, mind you. On the x-axis, for instance, you would have the velocity, but that's not how this is plotted. This is the usual way of plotting it. So the Reynolds number is on the x-axis, and on the y-axis is this quantity called c sub d, which is called the drag coefficient, and we have not even defined it at the moment, and we will define it in a minute when we start talking about the high Reynolds number law. Although, so as you can see, the Reynolds number goes from something like 1, so it's 1 here, it's 10 here, it's 100 here, and so on and so forth. So we are really, roughly speaking, anything above a Reynolds number of about 20 or 30 or so is considered to be high Reynolds number regime. And by the time, so there's a logarithmic axis, and by the time you go beyond a Reynolds number, you probably cannot see this. This is something like 10 raised to 5. Okay, so by the time you go beyond a Reynolds number is 10 raised to 5, which is really, really high, the character of this graph changes drastically. And so what is being plotted here is what's called the dimensionless drag coefficient, which we have not defined yet, and we will define in a minute, as a function of Reynolds number, and the contents of the Stokes law, this law, are essentially given by this dashed line here, this one, this thing called Stokes, this dashed line. So as you can see, at least from this graph, for low Reynolds number, the predictions of the Stokes law are, and so this solid line is I don't want to say experiment results of an experiment, but this is an idealized depiction of experimental results. Okay, experimental results are of course much messier. You'll have lots of data points, you'll have scatter and so on and so forth, but from a large number of experiments, this is the general behavior. Okay, so for the time being, for the purposes of this particular lecture, you can think of the solid line as being the the experimentally obtained line. And so this is the experimentally observed. The solid line represents the experimentally observed drag coefficient as a function of Reynolds number. And the main thing to note from this graph is that for relatively low Reynolds number, and the dashed line here, this dashed line, the lower dashed line, represents the prediction of the Stokes drag, and so for low Reynolds number, the experimental data confirms pretty well with the Stokes law. Okay, so that's the main thing to take away from this graph, although we haven't quite defined what the C sub d is and why the Stokes law looks like this. So we will come to that in a minute. So moving on, so we will now try to see what happens as you transition from low to high Reynolds number, right? So for something like low to moderate Reynolds numbers, say anything from 1 to about 20 or 30. In other words, when viscous forces are still important, remember the Reynolds number is the ratio of the inertial term to the viscous term, right? So if the Reynolds number is relatively low, then viscous forces dominate. Yeah, the flow is laminar, again, to quote an everyday experience, the flow of honey is generally laminar. If you think of the streamlines in a flow of honey, in motor oil or some such viscous fluid, they're generally laminar, they're not tangled. And as we said, the drag force is proportional to the velocity, which is what Stokes' law tells you. As the Reynolds number increases, viscous forces become progressively less important in the bulk flow. It's important to note this particular adjective, in the bulk flow. Okay, we're not talking about the boundary layers here. The boundary layer, complicated stuff, and we will touch upon it, but we will not go into any great detail of this particular aspect. Right. So, but again, a Reynolds number increases because the Reynolds number is defined as, it's worth writing this over and over again, right? As this increases, this means when the Reynolds number becomes larger, the importance of the denominator becomes progressively lesser, right? How will it become larger? Well, in many ways, maybe you're increasing the system size, the scale length, but that's not typically how, in everyday situations. If you increase the velocity, the Reynolds number increases, right? And so viscous effects become progressively less important in the bulk flow. Okay, we're not talking about the boundaries. We're not talking about a situation where, for instance, if this is a sphere and this is where the flow gets perturbed, right? This would be kind of the boundary layer, a very thin layer. That's not what we're talking about. By bulk flow, we are really talking about the undisturbed flow, right? So this is what we're talking about when we say bulk flow. Okay, right. So in the bulk, the flow is effectively inviscid. Same thing. We're saying the same thing over and over again in slightly different language. It's useful to do this so that you turn the concept around in your head and it gets embedded well. And as we said earlier, for a purely inviscid flow, right, for purely inviscid flow, the velocity can be given as a gradient of a scalar potential, right? And this quantity is called the velocity potential. Right? We've seen this. So the flow is effectively inviscid, in other words, potential. You can see this by looking at the Euler equation, which does not include the velocity. You can think of the Euler equation as the Navier-Stokes equation minus the viscous term. That's essentially what it is, right? So the flow is effectively potential far away from the body, okay, in the bulk flow, not near. But remember, and this is in boldface, it's a very important statement, the viscosity is still finite. It's not technically zero, okay, and the full velocity and not just the normal component needs to vanish on the surface of the object. What do I mean by this? Okay, you remember, for a potential flow, in other words, for a strictly inviscid flow, the tangential velocity can slip as much as possible, right? So the boundary conditions for a perfectly inviscid flow, if you want to specify the boundary conditions at the object, right? So you say that the normal velocity, so this would be the object, right? So the normal component of the velocity goes to 0, and maybe, usually you simply stick to that, and then you say that the velocity at infinity is equal to the undisturbed velocity. Okay, you don't specify any more components, any more boundary conditions. You specify only one boundary condition on the surface, and the other boundary condition is at infinity. Okay, you need two boundary conditions because the solution, you need to solve the Laplacian, right? So this is a second order differential equation. You need two boundary conditions. So one of the boundary conditions is typically specified at the boundary, and that would be the normal component of the velocity. You demand that the normal component of the velocity equals to 0, and the other boundary condition is typically specified at infinity, and that is a common sense boundary condition. It simply says that the velocity at infinity is what it would have been in the absence of the object. Because, very far away from the object does not exert much influence on the flow, right? However, you remember, this is technically valid only for a perfectly inviscid situation, and the combination of these two boundary conditions, when applied to the general solution, yields a solution where the flow is allowed to slip infinitely. The tangential component of the flow is allowed to slip infinitely on the surface of the sphere, and this predicts no drag at all, and this is the D'Alembert's paradox, right? But as we know, no flow is perfectly inviscid. Okay, it might well be true that the Reynolds number is large, and therefore viscous terms might be relatively not so important in the bulk flow. But remember, the viscosity is still finite, it's not technically 0, and therefore the full velocity, both, and the boundary conditions for viscous flow are that both the normal component as well as the tangential component vanish on the surface of the object. Okay, and so here right now we are not talking about this situation. Okay, so in other words, if both the normal and as well as the tangential component the velocity vanish on the surface of the object, this is essentially saying that the flow sticks to the object, which is what one would expect in a viscous situation. This is why you find that dust sticks to the blades of your ceiling fan, right? And that's because the velocity of the air right at the boundary, right where the air comes very close to the blade, it's technically 0. That's why the dust particle actually sticks. And well, there are some other things. I mean, the dust particles are oily, that increases the velocity, so that increases the viscosity. So it's not as if. So there are some other complications there also. Roughly speaking, this is what it is. In a viscous situation, both the components of velocity have to be 0 on the surface of the object. You don't bother about the boundary conditions at infinity, right? So this is what I meant by this statement, right? And which means that if the velocity has to come to a crashing halt right at the surface, the velocity gradient very close to the surface is quite large. The du dy is quite large near the surface, and therefore even if mu is small, as would be the case for a high Reynolds number situation, the viscosity is small, that's why the Reynolds number is high in the bulk flow. But this combination, this is a viscous stress, right? Mu times du dy. Because du dy is large, the combination mu times du dy becomes important. And where is it important? It's important in a thin boundary layer, not in the bulk flow, but in a very thin boundary layer near the object. Okay, and boundary layer theory was investigated extensively by Ludwig Prandtl. Prandtl also, I think it's the students of Prandtl who put together a book on fluid dynamics, a very nice, easy to read book. I would highly recommend this. Presents facts in a very, shall we say, intuitively appealing way. A little advanced, if I may say, but still, the facts are presented in such an intuitive way that it's well worth reading. So with that historical aside, we'll proceed. Right. So when we talk about high Reynolds number flows, in other words, say high velocity flows, for instance, the boundary layer apart, and this is very important, except for the boundary layer, okay, except for the very thin boundary layer around the solid object, the bulk flow is basically potential. Okay, it's basically inviscid. So viscosity is not important in the bulk flow, it's important only in the thin boundary layer around the solid object. Yeah, so the flow is basically potential, in other words, independent of viscosity. This is what saying the same thing. And so, if that's the case, this drag force that we talked about a little while ago Remember the drag in a low Reynolds number situation, we said that the Stokes law, which gives the drag force, predicts that the drag force is linearly proportional to the velocity, right? And the velocity there was the bulk velocity . And what's the bulk velocity? The bulk velocity is essentially the velocity that's far away from the boundary, from the solid object, okay? Essentially the undisturbed velocity, right? And so here we are again talking about the drag force, but for a high Reynolds number situation, okay? And now if you accept this statement that in the bulk the viscosity is not important, the flow is essentially potential. If that's the case, the macroscopic drag, which is essentially the drag felt in the bulk, if you will, there is no way it can depend upon the viscosity, right? It cannot depend upon nu or mu, as the case might be. Nu is simply mu over rho. So it cannot depend on the viscosity, because in the bulk flow the viscosity is unimportant, right? So the statement we're making is that for high Reynolds number flows, the macroscopic drag on a solid object must be independent of the viscosity. Okay, this is exactly diametrically opposite to the Stokes law, where the viscosity appeared. If you remember, there was a mu. Okay, so the drag force was proportional to low Reynolds number. The Stokes law said that the drag force was proportional to mu and to u, right? So the viscosity appeared, and this is just nu times rho, right? The viscosity appeared, but whereas here what we are saying is for high Reynolds number flow, because the bulk flow is effectively inviscid, viscosity is not important, this cannot be the law. In other words, the drag force cannot contain the viscosity. If that's the case, purely from dimensional analysis, there's only one way, and you can try this out, to construct a drag force that is independent of viscosity. Okay, to construct something with the dimensions of force using something that depends only on the density of the fluid, the dimensions of the object, say some L, if you're considering a sphere, the L would be, say, the radius of the sphere or the diameter of the sphere. It doesn't really matter, it's just a factor of 2, and the bulk velocity, because the bulk undisturbed velocity. So you have to construct a drag force only from these quantities. The viscosity cannot appear, because the bulk flow is essentially inviscid. That's the case, then there's only one way you can construct something with the dimensions of force, the drag force in this particular case, from these three quantities, and that is this way. So this is the high Reynolds number drag law. Okay, and I would say it's very different from Stokes law. Why is it very different? Well, first of all, there's no appearance of the viscosity, that's one thing. Secondly, if you remember, the Stokes law depended linearly on the velocity. The power here was 1, whereas here the power is 2. Very different dependence. Okay, and it's also been experimentally, so here you have the appearance of an L squared, which is kind of like an area. Okay, and it's been experimentally determined that in the high Reynolds number regime, the drag force experienced by an object is proportional to the cross-sectional area that it affords to the flow. Okay, and the cross-sectional area is something like L squared. Okay, now here's a situation where the bulk flow is essentially inviscid, and yet we are saying that there is a drag. Okay. As one would expect in a real life situation, there will be a drag even for the most low viscosity even for the most inviscid looking of flows, there will still be a drag on an object that you are trying to drag through this very inviscid fluid. Okay. Especially if you are trying to drag it at very high Reynolds number, there will be a drag. Yeah. The flow might well be potential in the bulk. Okay, but still there will be a drag, and that is because of boundary layer effects. Right at the boundary layer, even though the viscosity is unimportant in the bulk, right at the boundary layer, because the viscous stress appears in the combination mu times du dy, right, and because u, which is the velocity, has to come to a halt right at both components of the velocity have to become 0 right at the boundary. So the gradient of the velocity is very large. The velocity has to vanish from the bulk value all the way to 0 within a very small distance, and therefore du dy, simply because this y is very small, the y is of the order of the boundary layer thickness. Simply because it is very small, this gradient du dy is large, and therefore the quantity mu times du dy is appreciable even though mu itself is small in the bulk flow. Okay. And therefore there will be a drag, and that is due to boundary layer effects. Okay. But as far as the bulk flow is concerned, well, you have to construct a drag force that does not depend on viscosity. And the only way to construct something on the dimensions of force from something that depends only on the density of the fluid, the dimensions of the object, and the bulk velocity is this. And this is the high Reynolds number drag law, and it's very different from the Stokes law. And this proportionality constant is what's called the C sub d. We will come to that in a minute. And so this is the turbulent drag law. Okay, so I did not write this down on the slide. So this is called C sub d times rho L squared U squared, and this C sub d is the drag coefficient. And this was the quantity that was being plotted on the y-axis, and we'll come to this. So let's write this down here. The high Reynolds number, Now remember, I'm not writing a proportionality here anymore. I am writing the equality rho L squared U squared. Just this, right? And low Re, however, we had the Stokes law, and f of d was equal to some 12 times mu, and we had the u here, we had the L here, something like this. Okay, I hope I'm not making a mistake. Please verify this. Right. So now what we're plotting here is the Reynolds number on the very same graph that we saw before. We're plotting the Reynolds number on the x-axis against this dimension, and if you see, the combination of rho L squared and U squared has the dimensions of force. So per force, therefore necessarily this C sub d has to be a dimensionless constant, and that's what's being plotted on the y-axis. But you might wonder, for low Reynolds number, I thought there was no C sub d, right? There's no real C sub d here. So what's up? What we do is we essentially dig out a dimensionless drag coefficient for the low Reynolds number law by simply equating this to that. Okay, by simply equating this f sub d to that f sub d, and you can extract a C sub d, and that turns out, for this particular law, that kind of C sub d turns out to have this dependence against Reynolds number. Okay, so that's what's being plotted here. On the y-axis it's C sub d, and on the x-axis it's Reynolds number. Okay, so for low Reynolds number, if you simply equate this to this, that's not saying that the low Reynolds number drag law is the same as the high Reynolds number drag law. No, 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 no. I'm simply trying to extract an equivalent C sub d for low Reynolds number flows. Okay, and that turns out to be this dashed line. This dashed line here. Okay, and the solid line is an idealized version of experimental results, and it's seen to agree very well with the Stokes law. Right now, what happens at relatively high Reynolds number, say from about, this is about 10 right here. Okay, and this is something like 100, there's 1000, 10,000, 10 raised to 5, and a million. Okay, so what happens above, say about say 20 or so, something around here? What happens here? You see, the Stokes law is a straight line, this dashed line. If I extrapolate it, right, you start seeing deviations of this solid line from the dashed line. I'm not going to talk too much about this Ausin's law. We will, at the moment it's not terribly important for this particular discussion. So, but the main thing is this: the solid line starts to deviate from this dashed line, and the deviation starts at about Reynolds numbers a little larger than 10. Okay, something like 20 or so, right? So, and this particular behavior is given by the high Reynolds number law. If you were to plot C sub d as a function of Reynolds number, and for that I know the Reynolds number contains a nu, right? So if you were to, you cannot do it exclusively from this formula, of course, but if you were to introduce a Reynolds number into this formula by hand, making sure that the formula still remains the same, obviously, then you would be able to figure out how the high Reynolds number law behaves with how the dimensionless drag coefficient for the high Reynolds number law behaves with Reynolds number, right? And this is the experimentally observed curve, and clearly the experimentally observed curve deviates significantly from Stokes law, from the low Reynolds number law, beyond Reynolds numbers of about 20 or so. Okay, so as you can see, the drag kind of flattens out, it doesn't, and at very high Reynolds number there's a certain plummeting of the drag, which we will talk about in a minute. Okay, and yeah, so we will, let's go ahead. Yeah, so physically, having talked about this graph for a minute, let's now look at some pretty pictures. Encourage you to look up, say, Google vortex shedding, and you'll find plenty of very appealing movies, and this would be a snapshot from one such movie. With increasing Reynolds numbers, what happens is, so the flow here would be going from left to right, and what happens is there is a formation of vortices in the wake behind the flow. Okay, and this phenomenon is called vortex shedding, and it's believed that it's this phenomenon of shedding vortices that's central to the drag. Okay, and so it's the formation of these vortices that leads to the dissipation of energy, and the dissipation of energy is essentially due to a frictional kind of effect, which is what gives rise to the drag. And so as the Reynolds number of the fluid is increased beyond a certain critical Reynolds number, it's observed that such vortices are shed, and in particular, sometimes what's observed is the vortices start appearing alternately on both sides, and beyond a point, there's a certain symmetricity in the appearance of vortices, and these are really very beautiful images. And fluid dynamics has all kinds of computational as well as experimental depictions of fluid flow are really truly very beautiful. I encourage you to Google some of these, vortex shedding in particular, and you will. So I encourage you to explore this subject yourself. For the time being, I simply want to emphasize that it's this phenomenon of vortex shedding behind the solid cylinder, behind the object, behind this object, is this phenomenon of vortex shedding that is central to the phenomenon of drag at high Reynolds numbers. Okay, right. Now, going on to very, very high Reynolds numbers, right? So, going on to somewhere around here, going on to this region. Okay, these are Reynolds numbers in excess of 10 raised to 4 or 5 or something like that. Yeah, and so what we're going to do is zoom in, and here I will show you actual experimental results. So again, this is the Reynolds number being plotted on the x-axis, and this is the dimensionless drag coefficient being plotted on the y-axis. And so this is a logarithmic scale, and so this is something like 10 raised to 4 times 10 raised to 4. This would be something like 4 times 10 raised to 4. Okay, and this would be around 10 raised to 7. So this would be truly fantastically high Reynolds numbers, and these dots that you see are actual experimental results. Okay, so what's this graph telling us? Beyond about something like 4 times 10 raised to 5, there is a sudden plummeting of the drag. Okay, at very high Reynolds numbers, and this is taken from Achenbach, the drag suddenly plummets, and this is also a logarithmic scale. So this is really a substantial reduction in the drag, and this is called a turbulent drag reduction. And then there's a gradual increase in the drag beyond this critical Reynolds number. Why does this happen? This is really a rather complicated phenomenon. This is probably because people think that even at sufficiently high Reynolds numbers, at about the kinds of Reynolds numbers where these kinds of things happen, the boundary layer, which is this very thin layer around here, this would be the boundary layer. The boundary layer is still laminar. Okay, there's no turbulence. In other words, as you can see even from this very rough photograph, very old photograph, the streamlines are relatively laminar. There's no evidence for streamlines becoming tangled. Okay, whereas for super high Reynolds numbers, the boundary layer becomes turbulent. Okay, and the wake here, this becomes narrow, and in a complicated way, this is roughly why the drag force plummets, and this is what's called the drag crisis. Okay, and this is important because so we will return to the other aspects in a minute. So this is important because for instance, for supersonic planes, for supersonic flights, which used to be very popular, I think in the 80s, until it became commercially unviable because they consume too much fuel, and so it suddenly fell out of fashion. But supersonic flights, you go from relatively low Reynolds numbers where the Stokes law is valid to high Reynolds numbers where the turbulent drag law is valid. This kind of law, yeah, is valid. But if you keep increasing the velocity even further, between the Stokes law and this law, the behavior of the drag is relatively, there are no drastic changes, especially if you understand it well. You can tune your thrust that you're providing the aircraft, in accordance with this. But at really super high Reynolds numbers, what happens is there's a sudden reduction in drag. So when you're at really high speeds, the drag suddenly plummets, and this is something that you should be very aware of. Okay, the drag suddenly plummets, and so if you continue applying the same thrust, the results can be pretty unpleasant. So you have to be very cognizant of this fact, of this sudden drop in the drag, and your engineering has to take this into account, right? And so this is called the drag crisis. Why am I talking about this in an astrophysics oriented course? That's because, and this pertains to some of my research, and that's because, as I said, astrophysical fluids are often most of the time, astrophysical flows are in a very high Reynolds number situation. In particular, for instance, to take a concrete example, coronal mass ejections from the sun, when they're traveling through the solar wind, the Reynolds numbers for this situation are supposed to be very, very high, in excess of 1 million. Okay, in excess of about 1 million, right? And so we are essentially in the super high Reynolds number regime. So we have to realize that the drag law will probably be given by something like this, not by something like this, which would be this kind of law, and certainly not by the Stokes law, which is the low Reynolds number law. Okay, so we are, in particular, for the motion of coronal mass ejections through the solar wind, the relevant drag law should be something that's described by this. Okay, we might well choose to describe it with this kind of an equation. That's okay, right? But the drag coefficient that we extract should reflect the fact that we are in this regime. Okay, so hence this bit of emphasis on the super high Reynolds number regime. Okay, so having talked this far about Reynolds numbers and so on and so forth, we will next transition to calculating the lift of on an airfoil. I alluded to this some time ago. We simply said that we would appeal to something called the Kutta-Joukowski theorem. And this also has something to do with the Magnus effect that I also talked about. The reason why tennis ball, you impart top spin to a tennis ball and it dips, okay, or a cricket ball, when a spinner gives a vicious tweak to the cricket ball, there's a dip and that fools the batsman. And so we sort of discuss that in qualitative terms. We will come to that. We will discuss that in a little more detail. And the connection with the Reynolds number will become, the connection with the rest of this discussion will become apparent when we talk about it in some more detail. So that's it for now, and thank you.